Okay, so welcome everybody. Welcome to the second edition of the Ask Tom series about our spatial technologies. Right? Those of you who joined us 2 weeks ago, you will probably recall that we were talking about Oracle's Spatial Studio then. This time what we want to do is we want to go over the fundamentals of the spatial technologies. Basically to lay the foundation for more advanced and in-depth sessions, which we will be running in the coming months. For those of you who don't know me, my name is Hans Fiemann. I'm part of the Oracle Spatial and Graph product management team. And luckily, I'm not alone on today's webcast. My co-presenters are Ramu Murakami and David Lapp. I'm based over here in Hamburg in Germany. They're both over in the US on the East Coast in New England and Florida, respectively. So thanks for joining me on this session, and thanks for all the work you've already put into this. What we have on the agenda for today is what we have here. So what we want to do is we want to take you on a bit of a journey where hopefully in the end you'll have a good understanding of what spatial data typically looks like, how this is managed and analyzed in the Oracle database, and how you can deal with this kind of data either using SQL or using Python. And we'll also, towards the end, discuss setting up a sample geospatial platform using a reference architecture, which we have, so that you can try out things while we're preparing for the next session coming up at the end of this month. Okay, we have prepared and we will show 2 demo parts, one using SQL, the other one using Python. Of course, both working with spatial data. For those of you who are interested in a deep dive session about using Python with spatial data, we will definitely come back to this topic in a session probably in the month of April. And that actually brings me to a question about which programming languages you're using. Ramu, can you share the, correct, thank you. Can you share the poll? We've prepared a little poll. So if you would kindly let us know what your preferred programming language is to work with data in general or spatial data in particular. Is it Python? Is it R? Do you primarily use SQL or PL SQL for that matter? Do you use Java or anything else? Anybody using Go? Whatever. Okay, so I see the vast majority. Let me just quickly end the poll here. Let me just quickly show share the results. Okay, you're sharing results now, Ramu, are you?
Yes, I am.
Good. I just wanted to make sure we're not sort of interfering with one another. So interesting result, right? Pretty much everybody using SQL or PL SQL, but there's 20% of the folks using Python as well. That's great. That's a great fit for what we have prepared today. So let's jump right in. Briefly, let's have a quick chat about what Oracle Spatial is in the first place, just so that everybody is on the same page. Most people really associate spatial Oracle Spatial with the spatial capabilities in the database, but if you look at it more closely, that's actually not entirely accurate, right? Our spatial offering really consists of 3 parts. The first is, of course, the core spatial functionality in the database. Basically, anything to deal with geospatial data, essentially making use of the multi-model capabilities of our converged database, right? And just as a reminder, all of the spatial features are available free of charge in all Oracle database cloud services and all license bundles, okay? So that's the one thing. The second part is a number of components and APIs and services that make it simpler for developers to build spatial applications, right? So with these components, you can visualize maps, you can perform advanced analytics such as route calculations and so on. And even though some of these components, like the routing engine, are not an integral part in the database, but are deployed in an application server. They are still part of the database license so that you get them for free with every database. Okay, that's the second part. Third part is Spatial Studio, which we looked at in the last session, right? And as you will hopefully recall, the purpose of Spatial Studio is to make it simple for non-experts to get started with spatial technologies, right? If you use Spatial Studio, you don't really have to know all the technical details and all the syntax, the SQL syntax that we'll be talking about today, right? But of course, it helps to understand how these things work under the cover. And in particular, if you're a database developer, and looking at the ratio of folks on the call today who are using SQL to work with this kind of data, if, for example, you want to use SQL Developer to integrate the data that you have prepared and enriched with Spatial Studio into your application, then, of course, you will need to know the things which we will be covering in this session. So these are the things we want to be talking about. There's a bunch of other things which we will not be able to cover today, but which will be included in a future Ask Tom session. Okay, so that's the quick overview of Oracle Spatial. Core functionality in the database. What kind of data can we deal with? In the Oracle database, we can answer questions such as which properties are contained in a flood zone, which schools are within a mile of a hurricane path, where are the 5 nearest maintenance facilities, where can we deliver within 35 minutes? And that's interesting because that is potentially along the road network. Or where is the vegetation index of a specific region in a given country or state or something, using geo-referenced raster imagery, right? All of that functionality is available in all editions of the Oracle database, regardless of where it's deployed. So there's no longer the distinction between Oracle Locator as a feature and the Oracle Spatial and Graph database option. Right, and thanks for putting the link to the last session into the chat, Ramu, which actually reminds me, if anybody has questions, feel free to put them into the Q&A box. Kindly do not use the chat functionality just for us to keep track of questions and answers. Please use the Q&A box, and then we'll take care of that. We have, besides Ramu and David, we also have Jane Sharma as a panelist, so you can be pretty sure that you get a very solid answer from the team on whatever question you have in this context. Okay, right. So that's what we can do with Oracle Spatial, but how does that kind of data look like? What kind of data do we typically have? Well, we'll be talking about what is known as simple features in the industry in today's session, right? That'll be points and lines and line strings and polygons and compiled geometries made up of these elements. In the simplest case, points would be represented as latitude, longitude, like what we have here, for example, right? You have a table, you have a column which is longitude, a column which is latitude. And by the way, did you know you can create a spatial index directly on these columns? If you didn't, we'll show you in a moment, okay? Now, besides this sort of very rudimentary type of storage for points only, there's more things which we can do in the database. And one way of storing and managing and also exchanging data these days is to use JSON, or in this case, GeoJSON for that purpose, which is of course a great fit with the JSON features of the database. And Ramu will demo that in just a moment. There are other ways. The spatial industry has been very creative in coming up with all kinds of formats. There is what is known as well-known text, which is something which David will briefly touch on in his demo using Python. It's a bit older, but still useful. And then for data exchange, typically, or many organizations today use shapefiles. When we say shapefiles, right, that always sounds like one file per layer. There's actually several files, like what you can see here, right? The US interstates, that's 4 files making up the information, and you need all 4 of them to get a consistent, complete data set. As you will probably recall, Spatial Studio can handle this kind of data, right? And we showed that last time. So that's shapefiles. Then there's KML. That's a standard which Google came up with when they introduced Google Earth to better handle 3D data. And from the times when XML was hugely popular, we also have GML, which still today is being used quite heavily by, for example, the national mapping agencies and other authorities, right? We have support for all of these, right? So for us, the original representation of the spatial data doesn't matter much, right? In the different domains, weather or hydrography and so on. There's tons of additional formats, particularly file formats. But the good news is that there are tools out there that allow you to load these types of files into Oracle Spatial. Okay. One more thing, just quickly on spatial data. Spatial data sets do not only come in different file formats, but there's one more thing which is specific, namely the coordinate systems, right? Unfortunately, as you hopefully know, the Earth is not flat, right? So if you want to compute distances correctly, what you need to take into account is the curvature of the Earth. And so for so-called geodetic data, so data in a geodetic coordinate systems, that is exactly what we do, right? Most folks in this sort of geodetic domain are using a coordinate system which is known as the World Geodetic System of 1984, because that is also what your GPS device uses. But in many other cases, customers work with data sets that are already projected to a flat surface. Right? In that case, we need to know from the metadata associated with the data set you have, which coordinate system the data set is based on, right? So to cut the long story short, we can deal with a few thousand coordinate systems out of the box in the database, or you can define your own ones if you so wish, and we have functions to convert between them. But you need to tell the database which coordinate system you're using, right? Good. So that's essentially the intro. Anybody questions about spatial data? Now, if we put all of this together, then we'll end up with this, right? So this is essentially what spatial data look like in practice in the database, right? We have a database, a data type called SDO-geometry. And then in that data type, we need to indicate what kind of data is it? Is it 2D? Is it 3D? Is it a point? Is it a line? Is it a polygon? And as I was just saying, we need to indicate which coordinate system it has. And then for points, there's a dedicated SDO point type. Let me just quickly show you, right? An SDO point type, which is in here, right? Which allows you to specify just 2D or 3D points. For lines, line strings, and so on, data goes into V-arrays, because that's more than just 2 or 3 numbers, right? And bottom line is, for you as database developers, all coordinates, all these kind of pieces of information are accessible from SQL, right? But you need to deal with objects, so using the dot notation. If it's points, that's pretty simple. Or if it's V-arrays, like for lines and line strings and so forth, you need to make use of the table function, right? Good. Then we're already coming to the point where we're talking about querying this kind of data. Here's, oh, sorry, no, we're not quite there yet. We are, first of all, talking about metadata. So in order to quickly access data, we need a spatial index. And in order to create a spatial index, we need to provide some metadata. And that's, for example, the coordinate system information, right? And the minimum, maximum values in the 2 or 3 dimensions which you have. And if you look at the example here, this is what we need to insert into user SDO-geo metadata in order to make sure that the database knows what you're talking about and what the boundaries are and so on. There's one small thing here which is known as the tolerance, which is actually important because it's a measure, or it reflects the accuracy of the data. Now, what does that mean? If you have 2 points whether it be in a line string or just 2 individual points. And these 2 points are less than this value, less than the tolerance apart, then they are considered the same. Okay, and that's important for all kinds of geometric computations, but it's also important for validation, right? And we'll come to that again in just a second. So that's the metadata you need to have on the table, and then you can actually create your spatial index. Right, there's a create index, blah blah. Index type is spatial index, or these days our recommendation is to use spatial index underscore v2. It's actually mandatory for tables where you're using partitioning. And then the database will happily go ahead and create a spatial index, which is actually also reflected in a set of tables, or in one table where this data goes, the SDO index table. And if you query the metadata view here, user underscore SDO underscore index underscore metadata, this guy here, then you'll see, okay, this is the table, this is the column, this is the kind of spatial index, it's an R-tree index, and this is the table where it actually goes, and that is also visible in, for example, in SQL Developer, or in the data dictionary anyway. Now, I don't want to drill down into the topic of spatial indices too far, but the underlying idea is that we are creating bounding boxes around the different geometries, like what we do here, right? So we create a minimum bounding rectangle around every geometry. Why is that useful? Well, you can imagine if the rectangles are disjoint, then for any kind of spatial query, it's immediately clear that the two geometries are disjoint. So you don't need to do any complicated computation. You can always see immediately, okay, these two things, like this guy down here and that guy down there, the minimum bounding rectangles don't interact, meaning the two geometries are disjoint. Only when they are overlapping, then you need to actually look a little more closely and do the more complicated computation, look at whether there's any spatial interaction between the two, right? So minimum bounding rectangles is the basis for the spatial index, and then we take these, we aggregate them into higher level rectangles and more rectangles up to the root, and then if you have that, this is what an R tree looks like in principle. But I'll leave it at that, just so that you have an idea of why we have a spatial index in the first place. Okay, and when we have that, then of course we can access spatial data rapidly, right? Using the index and query and perform analysis, right? So there's a bunch of operators and functions that help you do this. Functions and operators to, for example, determine spatial relationships, right? Proximity, containment, and so on. Functions for aggregation, for performing all kinds of computations like distances and areas, or computing the buffer around a given geometry, and so on. And in today's talk, we'll primarily be looking at the inside operator, the SDO within distance operator, and we'll briefly touch on spatial data validation as well. Right, inside and within distance, Ramu will show that in a moment. For these kinds of proximity and containment queries, this is what a spatial query looks like. Right here, for the proximity, we have the operator, as I said, SDO underscore within underscore distance. First parameter is a column in a table. Second is the query window, and then there's additional parameters and options. So here you can figure out whether there are any objects within 20 miles of a given location, defined by geometry B, which is the warehouse with the name Dallas Warehouse. And you'll see that in Ramu's example in just a second. Similarly with the SDO inside, the one tricky thing which we've done here is just, if you haven't noticed, that we are using an index based on longitude and latitude directly, that is something we can achieve by means of a function-based index. And if you find that complicated, if you find all of the things which I've just been talking about confusing, my recommendation is simply use Spatial Studio. That covers the whole complexity of this under the covers. You don't need to deal with the metadata. You don't have to create the indices. If you have a table with latitude, longitude data, it'll happily create a spatial index for you on top of that. You can do the validation, you can do the data preparation and everything. So that makes it really simple. We're only showing this to you so that you can understand how to deal with it if you really want to do the lower level SQL-based computing and want to make use of the spatial data, which maybe you have uploaded using Spatial Studio or enriched using Spatial Studio in your application. Okay. Right. We'll come back to queries in the example in just a second. Before I come to that, just one quick remark on validity of spatial data, right? The geometries have to be valid in order to give consistently correct results. And there's a couple of things which can go wrong with geometries. I'm not going to go into the details here, but if you're interested in this topic and how to deal with incorrect spatial data, that can be, for example, the ordering can relate to the ordering of the outer rings of a polygon, for example, or all sorts of, or two points being too close to one another and stuff. If you're interested in that, I have written a blog post with the help of Alberto a while back, which you may find interesting, which is on the Oracle Spatial blog under the URL, which you can see on here. Okay. And Raul, thanks for posting the link to the blog here. That's great. Good. One more thing before we come to the demo. There is a set of utility functions which we have in Oracle Spatial, which you can use to deal with all the kinds of formats which I've been referring to earlier, right? How, converting to and from GeoJSON, working with well-known text or KML or whatever kind of other specific formats, GML, which we have, just so that you're aware that we don't really care much what the original data source is. We can pretty much deal with anything, and then you can use it in your spatially enabled workflows, right? Which brings us to the topic of the live demo. Again, if there are any questions in the meantime, feel free to put them into the Q&A box. And Ramu, if you want to just grab the screen, then you can go right ahead with the demo.
Awesome. Thank you, Hans. And hi, everyone. So in this demo, we're going to be running spatial queries and returning results in GeoJSON format. We will be using warehouses, stores, regions, and tornadoes as our tables. And all of these are located in Texas. We will assume that we've already uploaded our data and we configure the warehouse table using geometry columns. We've configured the store table using function-based spatial indexes, and we've also created our region and tornado path tables from a GeoJSON document. We are going to be exploring spatial queries that can help us answer some critical questions like which stores are locating within a particular distance from a specific warehouse, or how many tornadoes have passed through a certain region and the amount lost that has been created by that tornado in our region or around our warehouses. And finally, we're going to be covering how to return our findings in a GeoJSON format that is suitable for developers' integration. So let's go ahead and get started with our first queries. So right now I'm using the SQL Developer worksheet that is in the website browser, and you're able to access this through Oracle Database Actions under our autonomous database. And we're going to start by running some proximity queries. So proximity relates to how close items are to each other. And the main spatial proximity operators are SDO within distance, that returns items within a given distance of another. And we also have SDO NN, and N stands for nearest neighbor, and this returns the nearest item to another item. So let's go ahead and start with our first query. And this query is basically going to identify stores that are within 20 miles from our Dallas warehouse. So we go ahead and click run. And basically it returns 3 stores that are within 20 miles from our Dallas warehouse. Let's go ahead and run our second query. And I just want to highlight that we're using the SDO within distance, where we have to specify the distance that we want to filter by. So our second query is going to be using nearest neighbor. And basically, we're just trying to return the warehouse, the stores that are closest to our Dallas warehouse. And in here, we're using SDO batch size equals to 10. And this means that basically we're using a parameter that's going to specify the number of rows to be processed at a time when querying spatial data with the SDO nearest neighbor function. And it is basically used to improve the query performance by dividing the queries into smaller batches. And this helps our process be a little more efficient. So let's go ahead and run our next query. Our next query is basically the same. We're just showing the distance for these stores within nearest neighbor to our Dallas warehouse. So basically this means that we're returning the same 5 nearest stores, but we're also going to display the distance. So for example, for North Richland Hills, it is 13.92 miles away from our Dallas warehouse.
And that's a distance as the crow flies, right? So there's no computation on the road network here, but we'll talk about that in an upcoming session also, if anybody's interested in that specifically.
Yes, so let's go ahead and run our next query. And our next query is basically just filtering a little more the previous query, but we just want to show the retail stores that are closest to our Dallas warehouse. So as you can tell in here, we're only showing retail stores. So we're going to continue with our nearest neighbor operator, but in this case, we're actually creating a join. So we are trying to show our stores names and the warehouses names. And if we run this, we should be able to get the store and the nearest warehouse to this store. So this could be helpful in case we want to maybe optimize the way we deliver our content, or whatever we're selling to that store. So for example, here we know that Marshall should be getting content from the Dallas warehouse. And in this query, we're actually just showing the same content, but the same result, but we are also displaying the distance between these 2 points. So we're able to see how Marshall is 176.1 miles away from the Dallas warehouse. So in this next query, we're still using proximity, but we're going to go back to the within distance operator, and we're going to use aggregation analysis. In here, we're actually returning the number of tornadoes and maximum loss within 20 miles of the Dallas warehouse. So we are able to see how the Dallas warehouse has been impacted by 26 tornadoes, and the maximum loss has been $600,000. In this next query, we're actually returning, we're using a join, and we're going to run the following query to return each warehouse with the number of tornadoes and maximum loss within those 20 miles again. So we're basically showing all of the warehouses. And we're able to see our count and the maximum loss per warehouse. We can also alter the distance. Let's say changing this from 20 to 50, and we'll be able to see how the count and the maximum loss changes since we are increasing our distance. So we should be expecting more tornadoes and more loss. And right here, we're able to see how our count has increased for Amarillo warehouse, and we have our max loss in here displayed. So let's go ahead and move on to the containment queries. So containment refers to identifying items that are contained by a specific region or identifying regions that contain specific items. And the main operators are SDO inside, that returns items that are inside a region, and SDO contains return regions that contains items. But both of these operators do not return items that are on a boundary. We do have SDO any interact that returns items that are having any spatial relationships to other items, and this will include items that are located on a boundary. So our first query here is going to show all of the stores in region 2, and we're using SDO inside. So again, just a quick reminder, we do not include stores on a boundary in this query. And we're able to see how in here in region 2, we have 8 stores and they're all retails. Let's say that we wanted to show all of the regions with all of the stores. Again, we're using the SDO inside. And in here, we're going to be displaying the store name, the store type, and all of the regions. So this result represents all of the regions and all of the stores and the store names. So next, we're going to use the any interact operator for the purpose of aggregation of tornadoes by region. So let's go ahead and run this query. And this query is going to give us a count of all of the tornadoes in that region and the maximum loss. So for example, we're able to see in here that region 1 has had 19 tornadoes in total, and we see the maximum loss. And this is for all of our regions. So we have 20 regions in total. So let's identify regions containing tornadoes with loss over 100,000. We can go ahead and add this in our word clause. And this will only return the regions that have had those loss that is over 100,000. If we wanted to see the number of tornadoes that have impacted this region that has a loss of over 100,000, we can go ahead and also add the count property and run. And we're able to see that, for example, region 8 has had 2 tornadoes that has had a loss over 100,000. So we've gone over running spatial queries that involve proximity and containment. let's go ahead and run return our results in a GeoJSON format. So this is mainly a format that is preferred by developers for integration of spatial data. And we're going to start by running this query that is going to return tornadoes that has had loss that has more than $10 million. And in here, we're actually returning our geometry as a GeoJSON format. So right here, since we've used SDO_util.to GeoJSON, we've converted our geometry into a GeoJSON format. And next, we're going to use GeoJSON array aggregation function to convert the row of GeoJSON geometries into an array. And this is something that we need to build our GeoJSON document. So let's go ahead and run our query. We see here how we're using GeoJSON array aggregation. And here we have our GeoJSON array. So in this next query, we basically have to include both geometries and properties. So this query is going to go ahead and construct this for us for our array feature. And if we hover over the results, we'll be able to see the full results. And we're able to see our properties. For example, in here, we have the key of the tornado, we have the year that it happened, and the loss. And they're all over 10 million. We're going to use a GeoJSON array aggregation to compile the previous result into an array. So let's go ahead and run our query. And here we have our result. Again, we can hover over it to view the whole array. And to complete the construction of our GeoJSON document, we're going to include the top level keys that are type and features. So let's go ahead and run this. And here we have our GeoJSON document. So let's say that we wanted to share this with someone or integrate it in an application. We can just go ahead and copy this. And in this case, I just want to visualize my results. So I'm going to use a public website to display my results. In this case, I'm going to use geojson.io and paste the results of my query. And this is going to show my tornado lines. So again, if we click on it, we'll be able to see the properties of my tornado lines. And let's say that I wanted to add a buffer for my lines of 5 miles. I can go ahead and edit my query to include my 5 miles buffer. Let's go ahead and run this. And it generates a new GeoJSON document. Let's go ahead and copy this and create a new tab and paste our new result. And here we have our tornado with the 5 miles buffer. we have our new property right here too. And this basically concludes our demo. So in this demo, we've explored proximity and containment queries to derive insights from our spatial data. Specifically, we've used proximity queries like SDO within distance and SDO NN, so nearest neighbor, to determine the nearest warehouses to a specific store or to find all of the warehouses within a specific distance. We've also utilized containment queries like SDO inside, SDO contains, and SDO any interact that has helped us calculate the total loss of a particular region and the number of tornadoes that have passed through that region. And to share our findings with others, we've also been able to demonstrate how to return our queries in a GeoJSON format that is an easy way to share with our team or integrate in another application that consumes spatial data. So that's it for the demo. I'm going to pass it on to Hans.
Great, thanks a lot, Ramu. That was brilliant. I think at this point, David, next thing is we can jump straight to your demo. I think it was really nice to see how Ramu has built the JSON document from the ground up. For those of you who are not so comfortable, working with JSON, you could probably nicely see that first we just started with geometries, then we created features out of these geometries, combining attributes and geospatial data, and then combined these features into feature collections, which would then be, the complete JSON document, which Ramu could then use for anything like rendering on GeoJSON .io. Right, I think that brings us to the Python demo. David, do you want to take over at this point?
Yep, and I will let you confirm when you can see my screen, Hans.
Yeah, that works. Brilliant, thank you.
Yep, I'm just going to throw in another quick comment about kind of the context of what we saw. So what Ramu was showing was obviously just straight SQL, sort of, command line SQL access to asking all kinds of spatial questions directly, and just using the database and SQL to do that, and then constructing GeoJSON again, just through SQL in the database. And the fact that that sort of forms a good example of this converged Oracle database platform that supports not just the traditional relational data, but things like spatial, things like native JSON operations in the database, things like graph, and a bunch of other sorts of converged features. So the purpose of that demo was not to say that that's the only way that you can achieve those sorts of things. Like if you wanted to be able to create GeoJSON, if you wanted to see the results on a map, as we talked about in one of the Q&As, there is also this thing called Oracle Spatial Studio, which is a self-service tool, and it lets you basically ask the same kinds of questions Ramu was showing with SQL, but to do it through a GUI. And that same tool will also automatically expose your spatial data as GeoJSON if that's something that's important and you're not doing it straight through the database. Those sorts of capabilities exist in different places. However, it is, I think, really important and really valuable to understand that what Ramu was showing was that just with the database and the database alone, and like nothing else, you can achieve a whole bunch of sort of location intelligence, up to and including the ability to configure and expose the data in this sort of developer-friendly format. And then if it's convenient to sort of add other bits to the stack, that's great. But the database alone can do a ton. So what I'm going to show now is some examples of spatial mixed with Python and some Python libraries. And I think the context of this flows from what Ramu was doing, in that part of the broader point of being able to do all these things with SQL is that you can do them in something like Database Actions or SQL, SQL Developer Desktop or SQL Plus or your favorite SQL client. But you can also take advantage of those capabilities literally with any tool, platform, developer kit that can talk to the database and issue SQL. That's all it takes to be able to take advantage of these capabilities. Well, Python and machine learning and doing maybe spatial modeling and predictions and statistical analysis from the Python environment is just really one example of that general theme. And the context here in the example I'm going to show is where there's some work that we want to do with our spatial data in terms of sort of a data science flow, where we want to identify hotspots and cold spots using statistical algorithms that are not natively part of the database. There's part of some specialized Python packages, and we want to do that, but we're not going to bring an entire huge geospatial data warehouse into a Python client. We want the database to manage that information and to be able to summarize and distill it and be able to sort of dovetail with Python to be able to use these libraries. So that's what I'm going to show now. And I'm actually going to turn off my camera because I'm going to be looking at a different monitor. So where I am now here is in the Oracle OCI data science service in the Oracle Cloud, which is just a collaborative environment to run data science workflows and work in notebooks in this sort of collaborative environment. But everything I'm showing you would be sort of exactly the same in your own environment with Python in your own notebooks. So it all starts here with the ability to connect to Oracle database from Python. There was a library that was really, continues to be really popular called CX Oracle, which is Oracle's Python driver for connecting to Oracle database. It's recently been renamed Oracle DB, but it's the same, it's the same thing. It supports autonomous database. And it not only makes it easy to connect to Oracle database, but it has a lot of built-in capabilities to understand and easily use lots of features of the database, including data types, object data types like geometries and other advanced features of Oracle database without having to code them. So this is a great way to jump right into Oracle with Python. So I import that driver. There's some details here that we go into more in dedicated sessions on all this with some of the optimizations for how you configure that connection. But I'm simply going to connect to my autonomous database, which I've done now, and I'm going to create a what in CX Oracle DB driver is referred to as a cursor, so I can start to issue queries to the database. So just to make sure that the lights are on and someone's home here, I'm just going to do a hello world query and fetch the result. So here's my result. I know I'm now talking to my autonomous database. Well, one of the first things that's nice to do is to see what spatial data do I have. And Hans mentioned in his overview at the beginning how we store, before we create a spatial index, we create some spatial metadata. And that's just something that I can query. So I'm going to do that right now. I'm just querying my spatial metadata from Python, and it's showing me all the tables that I have with geometries. And so this sort of gives me a quick view of what I have to work with in this particular schema. So I'm going to pick one of those tables, which is parcels. And I know that I've got parcels in here. And I know that the geometry column is called geom. So I'm going to select a row from that table. But what I'm going to do is sort of continue with the theme that Ramu had at the end. I know that within Python, formats like GeoJSON and well-known text are going to be very important to make it easy to sort of subset and get bits of data from spatial based on maybe spatial queries, spatial aggregations, get it easily into Python where I can run with it using various Python libraries. So here I'm just going to run a query, which is going to select one of the parcel geometries, but I'm going to return it as GeoJSON. Now, Ramu showed using functions from our SDO-util, our utility package that can do things like return GeoJSON. There's also a set of methods on the geometry object type that can do sort of some of the same things. And I'm using this method called GeoJSON on the geometry in this case to get one of these parcels as GeoJSON, and here it is. So I've selected the category of this parcel, it's residential, and then the geometry as GeoJSON so that I could, easily get that into spatial. Now, not only can we just get spatial data in the format that we want in Python, but we can run whatever sort of spatial operations we want. So this is the same one that Ramu did when she got the buffers around the tornadoes. I'm going to get a buffer around a parcel. Just as an example of running a spatial operation. So where this was just the parcel geometry as GeoJSON, this is the buffer around the parcel as GeoJSON. So that's really just kind of the hello world of connecting to the database, issuing some basic spatial operation. And then really from here, and I should do a quick time check, from here on out, it really becomes a matter of what data do I want to get out of spatial? What sort of spatial operation do I want to do to get a nice sort of distilled subset of data for my machine learning algorithms? And then once I do that, then I'm loading various other libraries and running with it. And in this particular case that I will just sort of introduce, but not completely demonstrate, what I'm going to do down here is really just show that what the rest of this example shows is I've got a geodata warehouse full of historical car crash data. And what I want my spatial machine learning algorithms to do is to predict hotspots and cold spots for what are the areas where speeding tends to be where there tends to be more speeding involved crashes or fewer speeding, and where is speeding a major factor in really bad accidents, and where is it less of a factor? And that could obviously feed into various sorts of policies in terms of why that might be the case. But the interesting thing here is that what we do to feed all that is really just run a big spatial query. So what's in here is one of the operations that Ramu talked about, SDO any interact. So what this is doing, this one query is doing, is it's taking all this historical crash data and it's organizing it by summarizing the percent of crashes in each little gridded area around the country and determining what percent of the crashes in that little gridded area involved speeding. And so that's the kind of summary result that you would then go through the rest of this exercise and feed into the spatial machine learning models that can work with that kind of data. And you can also see here that I'm feeding it in using another one of those methods on the geometry object. In this case, instead of GeoJSON, it's well-known text. And I'm just looking here at the first few rows. So, very straightforward. And from here on out, it just becomes, a matter of loading some spatial machine learning libraries that we'll just take and run with this data. And eventually, which there isn't really time to do right now because we want to leave a few minutes for Q&A, we end up with maps showing us hot spots and cold spots and so forth. But it all starts with the fact that I have way more data in this geodata warehouse than I would ever try to load into memory and work with in a sort of a dedicated notebook session like that. I want to delegate the geospatial data management, sort of the scaling of it, the tuning, the security of it, and then use spatial operations like this from Python to do what we would call in this arena, like the feature engineering, the distilling and the summarizing of the data into a form where we want to just, again, run with it using some prediction libraries. And this whole thing here, this whole Python story, this is just one example of of the broader theme of managing your geospatial data in Oracle Spatial and then being able to access it in lots and lots of different ways, and this being just one. So Hans, I think that probably leaves us just a few minutes for Q&A.
Yep, great. Thanks a ton, David. That was really interesting. Okay, I hope you can see my screen again, just so that we can wrap up. Very useful, letting the database do the heavy lifting and then do the more advanced stuff in a Python client. Just a great way of getting work done. Before we come to a close, just one quick thing which I briefly wanted to touch on. If you are interested in trying these things out yourself, what Ramu was showing is actually part of a live lab. So I hope you are all familiar with the Live Labs platform, which we offer for all kinds of hands-on workshops. So Ramu, maybe you can paste the link into the chat if you haven't already done so, just so that folks can have a look at the work you've done in more detail in the Live Labs workshop. Alternatively, what you can do is you can use our reference architecture to set up a geospatial data platform. So,
hey Hans, before you say
yes.
that what Ramu was showing was our Cloud World Live Labs, and that
okay,
is on the cusp, but it is on the cusp of being
great. We're getting there.
Really.
Okay. Yes. Thanks for the clarification, David. Right. So one more reason actually to set up your own environment using the reference architecture. What we've built is, if you want to start quickly on OCI with our reference architecture, what we have, the idea is to give you a starting point for a cloud deployment, right? Enabling data preparation, enrichment, and data landing in an autonomous data warehouse. And from there, where you have the curated data, you're ready for either interactive analysis in Spatial Studio, or you can use that data warehouse as a basis for any kind of spatially enabled workflows, for example, using Apex or whatever, right? The great thing about this reference architecture, which you can find under the link which is on this slide, is it's published as Terraform scripts on GitHub, which means you can pull the code into OCI Resource Manager with a single click, create the stack, deploy it on the Oracle Cloud infrastructure, or if you don't like it the way it is, alternatively, download the code from GitHub to your machine, customize it, tweak it any way you want, and then deploy the final architecture using the Terraform command line interface, right? So that you would end up with something like this. And as I said, the automation exists. There's a button on the website which just allows you to fire up this whole environment, right? Really makes it simple to get started with this. And just because we're almost at the top of the hour, let me just quickly use the remaining minute for two pieces of information. One, if you're interested in this whole topic of spatial data, spatial analytics, location intelligence, and so forth, there is a dedicated spatial track that covers location, mapping, any geospatial topics in the Analytics and Data Summit, which is coming up in March in Redwood Shores in California. There's 5 sessions, a hands-on lab. The product team is there, so we'll have a couple of colleagues in Redwood Shores for you to meet, to discuss, to network, and so forth. There's a couple of additional tracks on machine learning, graph technologies, data lakehouse, analytics and BI, and so forth. So overall, it's more than 40 sessions. Oracle PMs are there, but it is not an Oracle event. It is organized by the analytics and data community, so it's the user group which runs it. We're supporting it in that it is happening in the Oracle Customer Visit Center. We've got, as I said, folks there, PMs, executives, there's partners there. Great opportunity for one-on-one meetings with us, and lots of content for developers, for data scientists, for business analysts, DBAs, LOB and IT managers, essentially all levels, right? It's a great opportunity to learn and to network. Talking about learning, where can you learn more about Oracle Spatial? Here are the most, from my perspective, most important links. I've been talking about the live labs already. Quick comment on the blog, on the blogs.oracle.com/Oracle Spatial. We still have older content, which is pretty much relevant, up, but we have moved to 2 new places. So all the general information is now included in the Database Insider blog. So under blogs.oracle.com/database, and there's a dedicated category for spatial. And for more detailed developer-oriented material, I suggest you go to medium.com/Oracle Devs. And before I forget, the community is essentially connected through the LinkedIn group, the Oracle Spatial and Graph LinkedIn group, the URL of which you can also find on this slide. Good. We're at the top of the hour. I think we have been answering questions pretty much as we were going along. Let me quickly see. There's a question from Chris about Spatial Studio and whether that is a replacement for the map visualization component. And the answer to that one is actually no. It uses the map visualization component as an integral part, but it is not a replacement. That Spatial Studio is actually an end-user self-service tool, right, geared towards the analyst and the developer. So we've got the 2 target audiences. If you want to learn more about it, we've covered it in the first session in this series, or the last session. The map visualization component is a set of APIs. So if you want to integrate map visualization into your a web application, we are offering a set of JavaScript APIs, and the map visualization component comes with its server that allows you to serve map tiles and so forth. That is the map visualization component. Okay. All right. In the interest of time, let me just quickly move on to the last slide I have, which is the save the date. There was a question earlier on about more information on the network data model and queries on road networks or rail networks for that matter, and so on. We will be talking about, and that's the sneak preview here, we will be talking about, or David Lapp actually will be talking about spatial data in conjunction with time as the 4th dimension. So spatial temporal data, right? Analyzing evolution over time using Spatial Studio, or rendering streaming positional data as moving objects, or a more in-depth look at like geofencing, contact tracing, and things you can do on streaming data. And as part of that, there will be the computations on the road network, or on the rail network, if you so wish, plus more details on what we call linear referencing in the industry. Okay, and we'll briefly touch on using time in conjunction with location for predictive analytics, kind of along the lines of what David was just showing in Python, right? So that's what's coming up on February 28th and March 1st. These are 2 different sessions, part 1 and part 2, because it's just too much content for one single session. So we have them back to back, end of the month and 1st of March. And there's more sessions coming up. So I hope you have subscribed to the Ask Tom series here, so that you get the up-to-date information on what's coming up. And with that, I hope it's become clear what kind of spatial data we can deal with in Oracle Spatial, what spatial data looks like in the first place, how we store it, how we manage it, how you can access it. We've been looking at different kinds of queries, different ways of publishing the data, setting up the reference architecture, and I hope it was useful and insightful. I'd like to especially thank Ramu for preparing the demo, and for David, really like myself, kind of jumping in at the 11th hour, taking over this webcast and the demo. So thanks a ton for that. Special thanks also to Jayant, who did the work behind the scenes with the Q&A as a panelist. And if there are no further questions, I think we can call it a day. Thanks a lot again, and I hope to see you all on the next Ask Tom session on the spatial technologies. Thank you.
Thank you, everyone.